Section 7.3 today, and you're almost done. Almost done. Okay, so today we're looking at work done by variable force. If you have a constant force, then work is simply going to be the force exerted on an object through a distance. Okay, so if you push on a car that's in neutral and you put a certain amount of force and you push the car through a certain distance and you're pushing in the same direction that it is moving, then you are exerting a positive force on it. If your car is in neutral and it's moving towards you and you're trying to push it so that it doesn't fall down the hill, first of all, get out of the way, you're stupid, but you are pushing against its distance or its displacement, then you are putting a negative amount of work on it and hopefully trying to impede its speeding up going down the hill. So we're going to look at the fact that if you graphically can show that the area under a curve is simply going to be whatever your x component is times your y. So look at this graph, simple graph. We have position on the bottom. So going from position 1 to position 2, that is a displacement. So that's d. So from area position 1 to position 2, that's a displacement. And if the force is positive and in that direction, now you have to make sure that it's in the direction of the displacement, but if you have a certain force, so let's look at F, you have a constant force, like let's say 10 or 100 or whatever it is, and you've got a force acting at 1 and a force acting at 2 and all the spaces in between 1 and 2, so it's moving through that displacement line, then the area under the curve is your work. Okay, so if you were to vary that force so that you push at 10 newtons and then you push at 2 newtons and then you push at 50 newtons, okay, so if you had something like this would be easy. So the different works at the different forces would simply be summed. You add them up. It's a summation of the variant forces at the different amounts. Okay, so if you knew you were pushing at 2 and then you pushed at 3 and then you pushed at 4, you could simply just take position times force, okay, force times distance, that equals work, and then have a new work with a new force, and then a new work with a new force, and then add all the works together, and the total of those works would simply be your variant forces acting through a distance. Okay, now you know that that's not going to happen very often, but what is going to happen is you could push, and as you're pushing, you push harder as you go. Okay, so you're starting to push, and you don't push at 10 newtons, you push at 1 newton going to 3 newtons, going to 5 newtons, going to 7 newtons. Or you can weaken out, fatigue, okay, you've got the barbell over your head, you're Mr. Macho, and all of a sudden your muscles are fatiguing, and then all of a sudden you cannot position it, so you put 10 newtons and then 3 newtons and then 1 newton, and in the meantime it's falling on your head. So that in that case, you're going to have something more like this. This is a variable force. Okay, so a variable force is when you have some kind of a J curve, so you don't have a linear. You have some kind of an exponential curve. Okay, so whether you have x squared or you have anything that you can describe that way, or it's a very complicated shape, like something from an oscilloscope, okay, or an EKG, where it's up and down in different speeds, and it's gaining slowly and dropping quickly and different things like that. That's a variable force. So even though this is way harder, this is still a simple example, because if you're pushing and as you're pushing harder. Okay, so from position 1 you were pushing at 5 newtons. By the time you get to position 2, you're pushing at 15, and it's increasing during that time. Then the only way you could approximate that is by taking teeny little slivers of position versus force squares, okay, and then adding those up. Well, that's what calculus is. That's the whole idea behind calculus. Calculus is taking tiny little shreds of rectangles and then adding them together. Okay, and the smaller your rectangles, the more it approximates the area under the curve. So look at the first picture. You've got nice thick triangle or rectangles, with lots of white spaces under the curve. That means that that's not, and you've got sticky out parts on one side and not enough on the other side. So you've got lots of empty spaces when you have big, hefty boxes. When you have thinner boxes, you have less white spaces and less rectangles that are sticking out on the other side, which are actually showing you've got something that's not actually there. Okay, so it's approximating better. So the idea behind calculus is if you can get that down to a very infinitesimally small, ridiculously so conceptually small limit, almost going to zero of dimension, but not zero. Okay, the tiniest little shred of a distance, and then add all those boxes up, the more and more and more refined it becomes, the more closer it approximates the area under a curve. Okay, so what we'll be doing in section 3 is work done by a variable force, and I can't do a lot with this section because I'm not going to do anything that requires calculus. All right, so there is many of these types of questions would require calculus, so the questions that I'm going to give you are the easier end questions of this section. All right, I hope you're doing well. I miss you.